Hi everyone, and welcome to my Calculus 1 and 2, or AP Calculus AB and BC review. In this lesson, we're going to be talking about, I'm going to aim to prepare and inform students who are learning or are preparing to learn Calculus 1 or 2, and to provide detailed information about each concept covered in both courses. So I just want to be able to explain many concepts of both Calc 1 and 2 with the best of my ability, and just hopefully you'll be able to understand. And notice these sessions are recorded, so this is just for your heed. Feel free to ask any questions about each concept, and I'll try to answer them as best as I can. So who am I? So my name is Praneet Chitrala here, and my hobbies are math, science, gaming, and tennis. Well, I love to I have extensively studied, thoroughly studied, and intensively studied high-level math and physics, and I love to learn and teach. So there are going to be 10 units covered in this course, and the first 6 are here. And each course will occur. This course is going to take the course of 10 days, and each unit is going to take 1 day. So the first unit is limits and continuity, and we'll go on from there. These are the other 4 units. So the first unit is limits and continuity. And this unit will describe how the patterns present in a function determine the behavior of the function itself. So the first unit is the limit definition. So what is a limit? So suppose you have a function like this, right? There is just some separation here. It's a normal function still, but there's just a separation there. So you can see that the function is defined at this point. Look at this shaded in circle. And this is not defined here. There's just an open circle. So yeah, the function itself is defined at this point, whatever it is. But what happens if we approach this x value very closely from either the left side or the right side? So that's when that's what happens here. So let's go very close. Let's go to this x-axis or x point from the left side. So you go very closely along this function path and reach the x value from this point, and you just get this. This is the left limit here. What about from the right side? Well, you go from the right side here all the way, follow the path, and then you reach this limit here. So this value. Let's just try with another equation here. So if we want to find out the limit for this x value right here, go from the left side. So you go all the way through the left side of this path and reach this point. Same with the right side. Go down this path, and then you reach this point. This is just a very simplified version, but I'll get to what the types of limits after. So there are essentially 3 types of limits: the left-handed limit, the right-handed limit, and the actual limit. There is no name for the actual limit, but I'm just calling it the actual limit just for now. So the left-handed limit, given by the name, is the limit as x approaches a from the left side. That's the limit as x approaches a from the left side, and that limit is the value of m. So the value of f of x as x approaches a from the left side equals m. Same with the right side. You approach the value from the right side. So the value of f of x as x approaches a from the right side approaches m. So that's this value here. And same with the actual limit, but this time it combines these two. As x approaches a from the left and the right side, the value of f of x approaches L. And you can see here how these limits are graphically represented. So the left-handed limit approaches the x value from the left side. The right-handed limit approaches the x value from the right side, and the actual limit approaches the x value from both the left and the right side. So now, what does it mean if a limit exists? So we're going back to the previous examples, right? So we have this function here. So as the limit as f of x approaches, suppose this is x equals a. If it approaches a from the left side, the limit is m. This y value is m. And the limit as f of x approaches x from the right side of a is equal to n. So this y value is n. But since they don't equal each other, like there's no one value that both sides go towards, the limit does not exist. On the contrary, for this function, as the limit approaches x, as the limit of f of x as x approaches a from the left side is equal to L right here, and same with the right side, the limit as x approaches a from the right side of f of x is equal to L. But since they're equal and they both approach the same value, the actual limit is also equal to L. So in other words, the actual limit is only true if the actual limit only exists if and only if the left limit exists and the right limit exists. So here are some examples for how limits can be determined. So let's calculate the limit of f of x as x approaches -1 from the left side. So using the the features of a left-handed limit, right-handed limit, and an actual limit, how would you determine this limit here? So the x value that we're concerned with is x equals -1. So you see here, even though it's defined at -1 is defined at 1.5, that's not necessarily the value of the limit itself. So wherever the function is defined does not mean that the limit will also equal that point. So let's see what point the limit approaches as x approaches -1 from the left side. So you follow this path here, and you get -0.25, and that's the value of this point right here. Same with the right side. You approach -1 from the right side, and then you get -0.25 again. Now, you want to find the actual limit of f of x as x approaches -1. So you have to find out the limit as the left-handed limit and the right-handed limit of both of these. And since they are equal, then this actual limit is also equal to -0.25. They both sides of the function approach the same value, so that's what the limit approaches as x approaches -1. Now let's look at 0.5, which is right here. If you approach it from the left side, you go right here, you follow this path, and then you get this point, which is 0.5, 1. So as a result, the limit is equal to 1, because that's the y value. But if you approach 0.5 from the right side, you follow this path, you instead get 2, because that's what this if you go from the right side, you will approach the value of 2. So this limit is equal to 2. But since the left-handed limit and the right-handed limit are not equal, then the actual limit does not exist. They don't approach the same value, and they don't approach a consensus, so they don't approach the same value, so it does not exist. So now we're going to talk about discontinuities. And there are essentially four types of discontinuities. There is a removable discontinuity, an infinite discontinuity, a jump discontinuity, and an oscillating discontinuity. So let's first talk about removable discontinuity. Yes. Yeah, it doesn't matter what the function is actually equal to. It just matters what the function is approaching. So like what's it going towards. Yeah. So yeah, don't always you will need to know when the function is defined, but you don't really it doesn't really need to be defined at the same point. Yeah, so just only only focus on the trend of the function. So removable discontinuity is is just undefined and or discontinuous at a single point, and it's also known as a hole. So because it looks like a hole right here, that's a hole, and it just this one point of the function displaced. So this is these are examples of a removable discontinuity, and this can be you can determine whether a function has a removable discontinuity if this limit applies. So if the limit of f of x does not equal f of the limit as f of x as x approaches a does not equal f of a itself, then you have a removable discontinuity. So you see the limit over here. So here f of a is not defined, so you can't really there is no way there's no way for there to be a point on this graph right at this x-axis, x point. But over here, you can see that the value of f of a, which is this blue dot here, is not the same as the limit, which is down here. So that means that, and as it's shown down here, the limit as at x equals a exists, but the actual value is not equal to the limit. And the limit exists. So the limit is a finite number, so it exists. But it's not necessarily equal to the value it's defined at, or f of a. A jump discontinuity, on the other hand, the limit does not exist, which which is shown by here. And I'll describe what a jump discontinuity is. It's a noticeable interruption in a function at a value of x. So you can see the function just jumps right there. It jumped, but notice that it's a finite jump. Like it approaches a finite value. It does not approach infinity or net positive infinity or negative infinity. So over here, it approaches like 2.5 or 1, but it's not going to infinity or negative infinity. And that's what's shown here. And that's important. It does not approach either infinities from the left side or the right side. No, from the left side and the right side. So both left-handed and right-handed limits are finite, though they're not equal, and meaning that the actual limit does not exist. Infinite discontinuities, on the other hand, show that either one of them, the left-handed limit or the right-handed limit, approaches in positive or negative infinity. And it's basically an infinite discontinuity approaches infinity at a value of x. It's also known as a vertical asymptote, and that should be a very familiar term by now. And you can see that x equals a is an asymptote here, and x equals a is an asymptote here. Yeah. So you can see that it's finite here, but there's one side is still going to infinity. So it doesn't matter, like it has either one can be infinite. It just has to have just either side, the left side or the right side, has to approach infinity. And said here, either one or both of the one-sided limits diverges to a positive or negative infinity. meaning that those one-sided limits do not exist. And if a limit approaches infinity, it's regarded as not existing. But it's just a specific example. And an oscillating discontinuity approaches numerous values undefined of y at a value of x. You don't know what value of y it's approaching. It can approach 0 here, or 1, or -1, or 0.5. You don't know. It just approaches some random value. And for that to happen, the limit as f of x as x approaches a does not exist, and f of a is undefined. So nothing exists. Nothing is defined. No, not the limit or the function. So here are some examples. Identify the types of discontinuities present in the graph below. So I'll give you some time, but there are exactly 2 discontinuities, but try to determine what the discontinuities are. So there are 2 discontinuities. Yeah, there is a hole at here. So that's what the removable discontinuity is. And you can also see a hole, or not a hole, or yeah, you can see a jump discontinuity here. So these are the discontinuities that you can see here. The jump discontinuity at this x value, and the removable discontinuity at this value. And now we'll look at the algebraic side. Identify what type of discontinuity is this. Yeah, so you can see that the left side and the right side approach infinity, but it doesn't matter like which one. So by the definition of an infinite discontinuity, either one of the left side or the right side has to approach infinity, meaning that this is an infinite discontinuity. Just the presence of just making the limit equal approach infinity makes it an infinite discontinuity. So now we're going to talk about end behavior. And instead of the limit itself approaching infinity, we're going to talk about how x approaches infinity instead. So what happens when x approaches infinity of a function, positive or negative infinity? So there are some important facts that you need to know before we get started. So the first limit, so if c is a constant and p is greater than 0, and this is important, then the limit as x approaches plus or minus infinity of c over x to the p power is equal to 0. The bottom is increasing much faster than the top, so that's why the limit approaches 0. Same with the so instead, no, not the same. The limit as x approaches plus or minus infinity of c times x to the p power, instead of being in the denominator, it's just multiplied instead. That approaches plus or minus infinity, and that really depends on whether p is odd or even. If p is odd, then it's either plus or minus infinity. But if p is even, it's either positive infinity always or negative infinity always. And lastly, the limit as x approaches plus or minus infinity of c, or which is a constant, is just c itself. And you can just see that in any constant. Now, fact number 2. If p is even, then the pth root of x to the p is equal to the absolute value of x. That's how the absolute value of x is defined in terms of radicals and exponents. And then fact 3 is that the limit as x approaches in like positive infinity of absolute value of x over normal x is equal to 1. But the limit as x approaches negative infinity of absolute value of x over x is equal to negative 1. And you can see that if you put a positive value for x in here, you'll always get 1. But if you put a negative value of x for x, you get negative 1. And that just, you can see that in maybe like a graph. Yeah. So now we're going to talk about the end behavior of rational functions. Yes, exactly. So like absolute value of x is always positive, but x can either be positive or negative. And that will define whether, the graph is positive or negative. So yeah, we're going to talk about the end behavior of rational functions. And this is a simplified definition of a rational function. But the only important terms that we're going to be concerned about are the leading coefficient, like the leading terms of the numerator and the denominator. So A is the leading coefficient of the numerator, B is the leading coefficient of the denominator, and M is the highest degree of the numerator, and N is the greatest degree of the denominator. So now remember fact 1. Like remember these limits here, because they will come in play later on. So case 1 is when the highest degree of the numerator is smaller than the highest degree of the denominator. Or in other words, the numerator is smaller than the denominator. If that's the case, then the limit of f of x, regardless of whether x approaches plus or minus infinity, is 0. Because the bottom is increasing much faster than the top. And one thing to notice is that I've disregarded the 3x minus 1 over here and the 2x here. That's because in either the numerator and the denominator, the x squared term is increasing much faster than 3x or negative 1. And the x cubed term is increasing much faster than the 2x term. So these terms can be ignored, and only the first two, the greatest terms are only matter. So you could just keep those in there. So as a result, yeah, exactly. And that you can only do that in limits, though, not in actual functions. Because in limits, you're approaching a value, so you're approximating what value you're going to approach. But with a function, it has to be exact. Yeah, you can't do that with functions. Oh, sorry. So you can just disregard these irrelevant terms, and then you get this limit right here, x squared over x cubed, and then you just simplify that. And 1 over a very large number would easily approach 0, because if you increase the denominator, you can just find out in like 1/2, like 1/3 is smaller than 1/2, 1/4 is smaller than 1/3, and so on. So if you increase the denominator of a fraction, it'll approach 0. The second case is when both degrees are equal. In that case, the limit is just the ratio between the leading coefficients. So the leading coefficient of the numerator over the leading coefficient of the denominator. So in this case, we have we still can ignore these irrelevant terms in the limit. So that's why this limit has none of the irrelevant terms or the smaller terms. And because of that, you can simplify the x squared terms right there. You cancel them out. And then you get the limit as x approaches plus or minus infinity of 2 equals 2. And that's how, that's the ratio of the leading coefficients as well. And see, you see in this graph here, this is the graph that was mentioned. Same with the graph previously. Yeah, this is the same graph as this. So you can see what value the limit approaches just based on the trends. So it's approaching very close to y equals 2. Now, if the degree of the numerator is higher than the degree of the denominator, then the function will easily approach plus or minus infinity, because the top is increasing much faster than the bottom. And if that's the case, then it'll easily become much greater than 0, or like any number. It'll go easily to infinity. So as seen by this example here, you could just take out the irrelevant terms, because the leading term increases much faster than the other terms. And then that means that the only terms relevant are the greatest terms on each side. So x to the 4th and 15x. And that's only happens at a limit, of course. You can only do that. You can only eliminate these terms in a limit. So taking the limit as x approaches negative plus or minus infinity of f of x, you get x to the 4th over 15x, and you simplify that. And now you have x cubed over the limit as x approaches plus or minus infinity of x cubed over 15. And that will equal plus or minus 15, plus or minus infinity, because as x approaches plus or minus infinity, x cubed will go to plus or minus infinity. And you can see by this example, as x approaches positive infinity, f of x goes to positive infinity. As x approaches negative infinity, the limit of f of x approaches negative infinity, right here. So now we're going to talk about the end behavior of rational functions again, but still this time with radicals. So we have these two extra terms. We have p is the the root of the numerator, and q is the root of the denominator. This time we should remember facts 2 and 3. So if p is even, then this becomes x, the absolute value of x. And yeah, we've gone over these two again. So this time it's a little different, but instead of having directly relating m and n, we include p and q as well. So I skipped over the fact that m over p is less than n over q, because if that's the case, then this limit will go to 0 again, because the bottom is increasing much faster than the bottom. So that's how, yeah, we can see here, if the top is much smaller than the bottom, then the limit approaches 0. So we could just go back here. And we have m over p because here we just have to so if you eliminate all the other terms, yes, you will be able to watch the recording. I will send that. Yeah, I will send that after the recording is done. So if you eliminate all of these other irrelevant terms, you have the root of p of x to the a times x to the m. And just with exponent laws, the root, if you have an x root, yeah. So if you have a root here, so the root divides the exponent. So if you have x to the m with root p, like if you have root p x to the m, then you can write it as yeah, let me get out a whiteboard here. No, I don't think you guys can see it. So yeah, if you have, just with normal exponent laws, you'll just get x to the m over p power. So that's why we involve m over p and then n over q. So this limit, it's going to be a little difficult to explain, but you have to also take the root of a and the root of b as well. So that's how you get this constant right here. If m over p is equal to n over q, then the limit as x approaches plus or minus infinity of f of x is equal to plus or minus p, like root of p, over the root of p of a over the q root of b. And this plus or minus occurs because of this, like these roots. So I'll explain further. So suppose we have this example right here. Ignore the other like irrelevant terms, 3x plus 6, because x squared increases much faster than these two. Yeah, these two, and then x cubed increases much faster than this -4. So in this limit, you can set up the limit right here, and then you have the square root of x squared over the cube root of x cubed. Now the square root of x squared, since 2 is an even number, the square root of x squared equals absolute value of x, and cube root of x cubed is just equal to normal x, because it can equal, cube root can either be negative or positive, but the square root can only be positive. So that's why the absolute value is there. And then based on fact 3, we can determine that this limit will equal plus or minus 1, depending on the value of the infinity. So over here, the limit as f of x approaches positive infinity is equal to 1, positive 1. And the limit of f of x as x approaches negative infinity is negative 1. And yeah, you can see these horizontal asymptotes here. And yeah, that's one. So yeah, those are the different end behaviors of this function right here. And similarly, if m over p is greater than n over q, then this limit will approach plus or minus infinity. So this time we can take out the irrelevant terms and then take out the irrelevant terms here and put them into this limit. So the limit as x approaches infinity of f of x equals this term right here, the limit as x approaches positive infinity. This time I excluded negative infinity because you see this square root here. You cannot take the square root of a negative number, or you can, but it will not be a real number. It'll only be a complex number. So the negative infinity is excluded because of the square root. Or the term inside the square root can be negative, but it shouldn't be negative. So only the positive infinity matters. And you can see here that anything after negative infinity, or like up to negative infinity, like that's negative. So any value that makes this term negative is undefined, because the square root of a negative number is undefined. So that's why the limit as x approaches negative infinity of f of x does not exist right here. But we'll go to the sorry. Oh, I didn't put up a gem, sorry. Yeah, I just closed down the gem. So the limit as x approaches infinity of f of x can be set up as this limit right here. And then you just have to, like, with some like algebraic manipulation, you get this term right here. But the thing is, as the square root of as this term approaches, as x approaches infinity, this will approach negative at infinity. So you have this negative here, and the square root of x cubed will approach positive infinity, and then negative times positive is negative. So it'll approach negative infinity. So now there are some special limits. So don't worry about the last one. This is just an interesting limit to think about. But the first two were going to be considered later on. For this would be this kind of would be mentioned in pre-calc, but not really. But these first two limits are important for the rest of calculus, or just because of a constant E, or which is known as Euler's constant. So E is prevalent in a lot of places, and this is just the definition of E. The limit itself won't be really be used, but you just need to know what E is. So now we're going to get to trigonometric limits. And first, we're going to talk about the major trigonometric functions right here. So there's sine, and there's sine, cosine, tangent, cotangent, secant, and cosecant. And each of these trigonometric functions can be said in terms of sine and cosine. So tangent is sine over cosine, cotangent is cosine over sine, secant is 1 over cosine, and cosecant is 1 over sine. But for this unit, we're only going to be concerned about sine and cosine. We're not really going to be talking about any of these other four. So let's before we go into some important trigonometric limits, I'm going to discuss the range of these trigonometric functions. And range is just the set in which set of y values in which the function can be in. So the highest value of sine for either of these, the range is between -1 and 1, meaning that the highest y value possible in this function is 1, and the lowest y value possible is -1. And that applies for both cosine and sine. So now limit number 1, the limit as x approaches 0. So this is just an actual limit, not just a left-handed or right-handed limit, of sine of a of x over ax is equal to 1, regardless of the value of a. So any value of a, unless it's 0, a cannot equal 0, obviously. But any value of a will allow this limit to be true. So let's just suppose a equals 1. If a equals 1, we have this function right here. And the limit as f of x approaches 0 from the left side, it closely approaches 1 from the left side, and same from the right side. It approaches 1. So the actual value of the limit will approach 1 as well. And you can see that here. It's not equal, it's undefined at 0, but the limit approaches 1 at x equals 0. Now for the second limit, a little bit more complex, but this time, the limit as x approaches 0 of 1 minus cosine of a of x, all over ax, is this time equal to 0. And if we set, and of course a cannot equal 0 again, but if we set a equal to 1, then we get this function. And the limit as f of x approaches 0 from the negative side is 0 right here, and from the left side. And the limit as f of x approaches 0 from the right side is also 0, meaning that the actual limit of this function is also 0. Now limit number 3 is the limit as x approaches 0 of sine of a of x over the sine of b of x equals a over b. And this time b is not equal to 0. A can equal 0, but b cannot equal 0 because it'll be undefined. So suppose we have a equal to 6 and b equal to 3. The limit as x approaches 0 from the negative side of f of x. Yeah, so just to calculate this term ratio right here, 6 over 3 is 2, obviously. So we see here from the left side it approaches 2, and from the right side it approaches 2. So that's that. As a result, the whole limit itself approaches 2. So now we're going to solve limits algebraically. So not just looking at the trends of a graph, but actually using the equations themselves to solve them. So this flowchart is derived from Khan Academy, but it essentially follows a simple flowchart. You always start by direct substitution. You find out whether you always plug. So if you have a limit right here, you have this limit right here. You always plug in 0 first to see if see what the value approaches. So yeah. So if x approaches a, then you just find f of a. And there are 3 values or 3 outcomes that can happen. The first and best outcome is when the limit is already found. So f of a equals a finite number b, and b is equal to a real number. In that case, you don't need to go further. You already found the limit. It's b. But if direct substitution results in an asymptote, where f of a equals plus or minus infinity, or which in this case b over 0, and b is not equal to 0, then the limit is plus or minus 0. But this time, there's a third option, which requires more work. If it approaches an indeterminate value, if f of a approaches 0 over 0, in that case you have to do more stuff. So you have to do there are 4 other options that you can do. So you would try factoring, you would try finding complex conjugates or rational conjugate pairs, or you would deal with trigonometric identities. And if everything else fails, or if there's no way to if it's difficult to solve it, then you use approximation. But after you do these, if you write the limit in an equivalent form, you go back to direct substitution, and then go over this flowchart again until the limit is found or you find an asymptote. So first we'll go over basic limit laws. So if we have the limit as x equals a, x approaches a of f of x equals m, and the limit as x approaches a of g of x equals n, then if you have the limit as x approaches a of f of x plus g of x, you could just separate the limits themselves. So you separate the limits out, and that just equals m plus n. You can just separate the functions away and then take the limit of each individual function. That's the same with the difference. The limit as x approaches a of f of x minus g of x. Yes, this class will go at the same time. It'll happen between 2 to 3 p.m. at Eastern Standard Time. So you can separate the limits, and you get individual limits. Yeah, no problem. And you get m minus n. Now with a constant, it's easier as well. You could just, if you have the limit of a constant times the function, just bring the constant out and then take the limit of the function itself. And then you get k times m. Now with a product, simple again, the limit as x approaches a of a product of 2 functions, separate the 2 functions, and then take the limit of each individual limit, each individual function, and then multiply those functions. So you get m times n. Same with a quotient. If you have a limit of a quotient of functions, take the limit of each individual function, and then divide them. So m over n. Now we have a power of a function. So limit as the limit of a function to the n power, you just take the limit of the function itself and then raise it to the n power. So n to the n power. Same with the root. Yeah, the root and power are similar, so you could just take the limit of the function itself, and then take it to the nth root. So n root n. Now composition is a different thing. It's a little more complicated, but in this case, f of g of x, the limit of f of g of x, is equal to you first have to take the limit of g of x, but then you put the value of the limit inside f. You don't take the limit of f at all. You just have to take the limit of f. No, you just have to take the limit of g and then put that value, substitute that value for f of x. And if this only occurs if f is continuous at the value of this limit. So it's a little complicated, but yeah, just with some examples it'll help. So factoring, we're gonna start with a factoring example based on these previous equivalent forms. So we can factor this the numerator and the denominator into this. So yeah, you can cancel like terms. So the top numerator gets factored into x minus 1 times x plus 2. And the denominator gets factored to x minus 1 times 2x plus 1. This term can get canceled from both the numerator and the denominator, and you're left with this limit right here. Usually, if you do it in a normal function, you'll have a whole. But since the limit at a whole doesn't really matter, it doesn't really equal to the actual function itself, you could just ignore the whole. The whole would be at x equals 1, by the way. And then by direct substitution, you could just plug in 1 for x, and you get 3 over 3 equals 1. And I forgot to say that before you do this, you should check that this equals 0 over 0. And if you plug in 1 for this function right here, you will get 0 over 0. So rationalization and finding conjugates. So you can just find the rational conjugate of the numerator here. So if you plug in 4 for this, you get 2 minus 2 over 4 minus 4, and that's equal to 0 over 0. So you have to use rationalization. You have to use rationalization and a conjugate. So find the rational conjugate of the numerator and multiply them by both sides. And you can simplify it to get this limit right here. You can cancel out the x minus 4 term on both sides, and you're left with this term right here. Now with direct substitution, you can substitute x equals 4 for x, and then you get 1 over square root of 4 plus 2, and the square root of 4 is 2, and 2 plus 2 is 4. So you get 1 over 4, and that's the limit of this function right here. Now there's also a common denominator. I didn't put it in the flowchart, but this is also another way to write it. This is also another way to find an equivalent form. So if you substitute 9 for x, you get 0 over 0. So 9 minus 9 is 0, and then putting 9 into this term gets you 0. So 0 over 0. So then you substitute you multiply 5, you try to rationalize both this function. because you don't want a nested fraction. You don't want a fraction inside of a fraction. So you try to simplify this, and you get this term right here. And then you just simplify even more to get 5 times x minus 9 times x minus 4 all over minus x minus 9. You can simplify, or you can eliminate the x minus 9 term, and you're left with negative 5x times x minus 4. Using direct substitution, you can substitute 9 for x, and that will get you negative 25. So this limit is equal to negative 25. So in summary, for a common denominator, you have to essentially eliminate the nested fraction, a fraction within a fraction. And you want to make it so that it's just a clean, you just want to make it clean. So no fractions inside the fraction. Now, trigonometric identities, these ones are a little more complicated because you have to know which identity to use and when to use them. But let's use the simplest one, the Pythagorean identity. And this is just manipulated, but cosine squared of x is equal to 1 minus sine squared of x. So you could just substitute that for the cosine of x, cosine squared of x. And then you can factor this. You can factor 1 minus sine squared of x to get, you can factor it to get negative sine of x minus 1 times sine of x plus 1. And then you can eliminate the sine of x minus 1 term on both sides. And then you're left with this term right here. And using direct substitution, plug in pi over 2 for x. And sine of pi over 2 is equal to 1. 1 plus 1 equals 2. And then negative, you have the negative here. So the limit is equal to negative 1/2. So the last unit we're going to be talking about today is continuity. So what does it mean if a function is continuous? So you've probably heard of the word continuous or continuity before in math class, but essentially, in theory, the function looks like smooth. It just looks continuous. There are no breaks in it between. There are no jumps or like missing values. It's all values are defined. But in terms of calculus, there are three steps to finding whether a function is continuous. So first, the left-handed limits and the right-handed limit are equal, which means that the actual limit exists. And it not only exists, but it's equal to f of a itself. So this is the definition. This defines whether a function is continuous or not. If this limit exists, the actual limit exists, and it's equal to f of a. So you can see here that the function is continuous at x equals pi over 4. This should be x, but not y. And it's just equal to, just for now, it's just equal to square root of 2 over 2. So you can see that the left-handed limit exists. The left-handed limit is equal to the right-handed limit. So the function exists. The actual limit exists. And the actual limit is equal to the function value here itself too. So that's how and since they're equal, this function is continuous at x equals pi over 4. So let's see an example. Is this function continuous at x equals 0? So to find that, let's find out what f of 0 is. So just simply plug in 0 for x. Sine of 0 is 0, and e to the 0 is 1. So we know that f of 0 is 1. But let's find out the limit as x approaches 0 of f of x. So this limit, so the plus or minus, the left-handed and right-handed limits are equal, you can just find that out here. So you just plug in 0 for this into the limit using direct substitution, and you can see that this is also equal to 1. And since the limit is equal to the actual function value, you can see that this function is continuous at x equals 0. Now I'm going to talk about two different theorems, two important theorems for calculus. And the first one is known as the intermediate value theorem. And if the text is green, that means that I'm going to introduce some theorem or some theorem or an important fact. No, theorem, a certain theorem, and if it's yellow, it's going to be an important fact. So if f of x is continuous on the interval, the closed interval a, b, and L is any value between f of a and f of b, then there exists a value c such that c is between a and b, and f of c equals L. So essentially, if you so if f of a is less than f of b and a is less than b, then you have to have gone through this point at some point, like at some value c. You had to have gone past this value L. So an example, does there exist a value c on the interval where f of c equals 5? Or in other words, in this interval, does f of x equal 5 at some point? Does it equal 5 at some point? And wait, sorry. Yeah, this function is continuous, and it's known that sorry for this disturbance. It's known that f of 1 is equal to 2, so you just plug in 1 for f of x, and you get 1 minus 1 plus 2, and that's equal to 2. And f of 3 is equal to 8. Plug in 3 for f of x, and you get 8. And it must be known that f of x must be continuous for this to work. It is absolutely important that f of x is continuous. So we have this value here, interval. 1 is less than or equal to c, and is less than or equal to 3, meaning that f of 1 should be less than or equal to f of c, which should be less than or equal to f of 3. So we're assuming that because this is true, this will be true. So since f of 1 is 2, f of c would be equal to 5 at some point for c, and f of 3 equals 8. And that's a true statement. That means that there exists a value c on the interval where, on this interval, x is between 1 and 3, where f of c must equal 5. And in this case, it's xc equals 2. So you can just plug in 2 for x, and you get 5. Wait. Yeah, wait. No. It might not be 2, but yeah, it would be there. It's something else. I just made this a mistake. But there must exist a value c where f of c equals 5. Now you can also use it to find whether a function has a root on an interval. So we're going to show that the function f of x has a root on the interval 0, 1, between 0 and 1. So basically, and just to recap, a root is a value of the function, like an x value, where f of x equals 0. So we're going to find out where, like, the places where f of c equals 0. So we know that this function is continuous because it's a polynomial. Like, all polynomials are continuous, and you can just find that out. And it's known that f of 0 equals -9, and f of 1 is equal to 2. So by add a root, I've explained what a root is. So f of x equals 0, meaning that there exists a value c where f of c equals 0. And this will find any value of c. So if there's a value of c, then that value of c is the root. So we make this interval here. 0 is less than c, which is less than or equal to c, which is less than or equal to 1. And then you set that interval up, this interval for the function. F of 0 must be less than or equal to f of c, which must be less than or equal to f of 1. Meaning that -9 must be less than or equal to 0, which must be less than or equal to 2, and that is a true statement. Therefore, there exists a value of c on the interval where f of c equals 0, and therefore there is a root on f of x. There's at least one root on f of x on the interval 0, 1. Well, before I go into the other one, if this interval is not true, it doesn't necessarily mean that. So if f of c is not, like, if this interval does not become true, it doesn't necessarily mean that there's no c. It's just that you can't really determine it at once. So if you go back here, you can't really. It can still happen. You just don't. You just can't prove it with this, with this theorem right here. But don't worry about that too much. Now we're going to talk about the squeeze theorem. And the squeeze theorem is just a way to find difficult, find the value of difficult limits. So suppose that g of x is less than f of x, which is less than or equal to h of x. And you can see that here. If the limit as x approaches a of g of x is equal to the limit as x approaches a of h of x, and that those limits are equal to L, then the limit as x approaches a of f of x must also be equal to L. And you can see that here. Since the functions squeeze together so much and they approach the same value, that f of x also has to approach the same value. And this interval is true for all values along the selected interval. So suppose we have this limit right here. We have the limit as x approaches 0 of this function. So now always remember, use direct substitution first. I don't do that here, but yeah. If you have 0 times, it's undefined for now, but yeah, it's an indeterminate term, but we don't know the value. It's 0 times some undefined value. It can be infinity or 0, but we don't know. So this one is a little bit difficult to with squeeze theorem, you need to know exactly what you're doing. So you need to know how you're going to solve it and which things you're going to solve, or which equations you're going to use for g of x and h of x. So we know that we could set g of x equal to -1 and h of x equal to 1, because we know that the range of any sinusoidal, the range of a sine function is between -1 and 1. So we know that this sine of 1 over x must be between -1 and 1. And then you just want to try to get this function right here. So you just multiply x squared on both sides to get x squared times sine of x, sine of 1 over x. So then you can take the limit of all of these sides. And then since the limit as x approaches 0 of -x squared is 0, and the limit as x approaches 0 of x squared equals 0. You could just substitute those in. So yeah, you could just substitute 0 for both sides. And since this function, the limit is less than or equal to and greater than or equal to 0, the only way that the only function, like the value that this limit can be, is 0. If a value of, so suppose you have a limit, if the limit is less than or equal to and greater than or equal to some number, it has to equal that number. So therefore, the limit is equal to 0. So now a review. We went over these 6 units right here. We went over the limit definition, the types of discontinuities, end behavior, trigonometric limits, solving limits algebraically, and continuity. So thank you for attending my my first lesson, like the first unit lesson on calculus 1 or 2. And tomorrow we're going to go over the second unit, which is differentiation, like the definition and fundamental properties of differentiation. So if you have any question, please email me at this email, and I will send this. I will send this like recording on the email on the website, so anyone can view that if they want. So that's it for today, and thank you for joining me. And I'll see you hopefully tomorrow. Yep. Have a good day, guys.